Okay, so good afternoon. Welcome back to the weekly live sessions on mechanics and control of robotic manipulators. I am myself John. I am the TA for the weekly sessions, TA handling the weekly sessions for mechanics and control of robotic manipulators. So this would be the discussions on week 6. We have previously covered all the topics from regarding week 5. Uh, Until now, we have discussed all the topics regarding the geometric modeling. We have also discussed topics on kinematic modeling. We have discussed what is inverse kinematics. We have seen what is forward kinematics. How do we solve inverse kinematics problem? We have also seen the topic of robot singularities and how to determine the singularities of robotic manipulators. We have also seen the static modeling of robotic manipulators, regarding how much force do you need to exert on the motors so that the robot will be in static equilibrium. We have also seen the dynamic modeling of robotic manipulators so that when the robot is moving with all its masses and with all its inertia, how much force should we should be applying through the motors so that the robot will track the desired path. So after all those topics, now we move on to the topic of trajectory planning or various methods of how to plan a trajectory of a robot, because it basically deals with how you define the motion of uh, a part or any specific point of a robot which moves from one point to another point as a function of time. So like it could be done in a lot of ways. Infinite possible number of ways, but not all of them are actually feasible. Like for example, if you have an initial position like this, xi, and if you have a final position like this, xf, and if you try to plan a straight line like this, maybe a straight path with a constant velocity, something like that. So the problem with this is that if you consider the accelerations of something that is very straight, it will have sudden accelerations right at the beginning and right at the end. So that may not always be practical, or it may not even be very good for the motors and actuators. So there are a lot of schemes that we would commonly employ in case of planning a trajectory so that the robot can move from a start point to the end point. So like we'll deal with a few key definitions of trajectory. These are actually borrowed from the lectures of Professor Shantakumar. So basically, what does this about the topic trajectory covers? So the first point is during robot motion, the robot controller is provided with a steady stream of goal positions and velocities to task. So like if it has to move from one point to a final goal point, all its intermediate velocities, positions as a function of time, it's constantly provided as a stream of instructions to the robot. So the specification of robot's position as a function of time is called robot's trajectory. So like for example, if a robot tracks a path like this, so it starts from an initial position to the final position. So it can go from this initial position to the final position however it wants. Maybe it can go with a constant speed like this, or maybe it can start very slowly, and once it reaches some intermediate point, it can go very fast, and just before it stops, it can decelerate, very gradually. All sort of possible ways are possible, to go through this path from start position to end position. So it is when the time comes, of each and every position along this path as a function of time. That is where we define it as a trajectory actually, when time is also affected. So that is about trajectory. The key definition is the specification of a robot position as function of time is called trajectory. And now we go on to move on to topics on trajectory generation, how to generate various trajectories, relevant trajectories. So again, another definition of trajectory is nothing but it's a time history of position, velocity, and acceleration of this end effector or actuator joints. Like for example, if you only have a single link robot like this with a revolute joint, you can consider it to be a single link robot like this. And it is attached to the ground by a single rotary joint like this. So you can either define the trajectory along the through the task space, maybe theta, or you can define the trajectory with respect to its joint space xy. Either definitions are possible. We'll see the intricacies of either of these methods of trajectory planning. So the first one is called trajectory planning in joint space, where we define theta as a theta dot, and theta double dot as a function of time. The other scheme, we call it as task space trajectory planning, when the trajectory is planned on task space, where the position, velocity, and accelerations of task space are specified as a history of time. So the easiest or the most straightforward trajectory planning is what we call as a straight line interpolation. Right? We have a desired position, or it could be a joint variable, anything. Like if you want to move a joint variable or task space variable from an initial position to a final position, we can use this straight line interpolation. Just a straight line interpolation without any bells or whistles or any frills, something like that. So the basic expression for a straight line interpolation is nothing but this. You know, we are very familiar with the straight line equation. Y minus y0 would be y2 minus y0 by x2 minus x0 multiplied by x minus x0. This is similar to a straight line. This is exactly a straight line equation similar to y minus y0 is the slope times x minus x0. The very familiar straight line equation. So instead of y, we are actually interpolating this joint variable or task space variable x, and our independent coordinate would be t. So that's about it actually. So like simply rearranging the straight line equation to our context, we'll get this interpolation actually. So if you are given a final position, and if you are given an initial position, and you are also given the time to reach from your initial position to the final position, how do you interpolate the path? You can do that using this straight line interpolation. So with this information, for any time between T0 and TF, you can define, or you can actually find out the position, velocities, and accelerations using this interpolation. So that is one way of generating a trajectory, which is basically a straight line. Another trajectory generation, instead of a straight line, is what we call as a cubic polynomial interpolation. Instead of it being a straight line, we can actually interpolate it as a third order polynomial, or we call it as a cubic polynomial. So the reason for this is that if you take a look at if you take a look at this straight line interpolation, what will happen if you determine the velocities of this thing? So this is a first order curve. To get the profile of the velocity, if you take the derivative of the straight line interpolation, you will get a constant velocity curve, right? So initially, it won't have any velocities. It will jump up suddenly to a constant velocity. Then it will move from its initial velocity all the way. It will maintain a steady velocity, and suddenly it will drop to zero when it reaches its final position. So if this is the velocity profile for a straight line interpolation, how will the acceleration will look like? So if you take a derivative of this constant, acceleration would be zero between t0 and tf. But due to this sudden jump in velocities from t0, instantaneous jump in velocities, the acceleration will have a huge infinite accelerations, right, at the start and at the end. And along between T0 and T0 and TF, it will be zero. Zero acceleration, but it will have infinite jerks or infinite jumps at the boundary points. So that is not very desirable if you are designing a robot to have sudden or steep accelerations right at the beginning and at the end. It is never a good idea to plan something like that, because it can cause damages on the robot, all the controller electronics. It may not be even good for the motors actually. It may try to draw even more current because of this sudden demand of acceleration. So a solution for that is to plan a cubic polynomial or a cubic trajectory, which is, as you can see, it's much smoother than a straight line interpolation. So it begins very slowly, gradually it picks up its speed. Then as it reaches its goal position, it gradually decelerates, and it gracefully converges, or it gracefully reaches its final position. So if the position coordinates are a third order polynomial, how would the velocity look like? So if you take a derivative of a third order polynomial, velocity would be parabolic, like so. Right? It will be like so, like a parabola, and acceleration would be something like this. It will be like a straight line, very finite. That's how acceleration is going to look like. So you won't get any sort of unexpected jumps or jerks. So in that regard, it's much more smoother than that. So you can basically define a cubic polynomial like this. X of t is a constant, a0 plus a1 multiplied by t minus t0, a2 multiplied by t minus t0 the whole square, a3 multiplied by t minus t0 the whole cube, where t0 is the initial position. So normally we would consider t0 to be 0 because we always consider our trajectory to be starting at time t equal to 0. So our initial conditions, you can basically write your cubic polynomial something like a0 plus a1t plus a2t square plus a3t cube. You can also express it like that. So the question is, how do you find out these constant parameters a0, a1, a2, and a3? So these constant coefficients are basically a function of your initial position, the final position, and the time that you require to reach from your initial position to your final position. So to solve this, there are four coefficients, actually four unknowns. This is 1, this is 2, this is 3, this is 4. So to solve this problem, you will need four equations so that you can solve these four unknowns. So in that regard, you can have these boundary conditions. The boundary at time t is 0, uh, x at t equal to 0 is x0, the initial position. And if you have an initial velocity, x dot of t0 is x0 dot. You will get this expression for velocity if you take the derivative of x of t with respect to time. And same in the case at the end position. You will have x at t equal to tf as xf and x dot at t equal to tf as x dot f. These are your requirements. Right? Initial position, initial velocity, final position, and final velocity. That would be our requirements. And we should also note that we can only support boundary conditions up to velocity. Position and velocity is at the initial point, positions and velocities at the final point. We cannot support any requirements or any conditions on accelerations. For that, we may need to go for higher order polynomials. For now, for the time being, if you are using a cubic polynomial, we can satisfy our constraints on initial position, initial velocity, final position, and final velocity. We can afford up to velocities. So if this is the case, how do you solve? The way to solve this is that if you arrange these equations as a set of matrix and vector form, like so, you can solve for these coefficients by inverting this matrix and multiplying with the boundary conditions. So in the examples that we are mostly following, we consider the initial time t0 to be 0 and initial velocity x0 dot and the final velocity xf dot to be 0. So in most of the cases, our requirements would be, our requirements would be posed like this. We start from an initial position as, I'll call this as x0. Our final position would be xf. And the time to reach from initial to the final position would be specified as tf. So if these are our requirements, and we always consider our initial and final velocities to be 0 because the robot or the joint basically moves from zero velocity, and when it reaches its final position, it will also stop moving with 0 velocities. So if you plug in these conditions, actually, initial position is x0, that is this first equation. Initial velocity is 0, that is this second equation. Final position is, final position is this one, xf, and final velocity is 0. And time required is tf. If you invert this matrix and multiply to this equation, you will get these coefficients. And the coefficients are labeled over here like this. Right? So if you write that equation for the trajectory in terms of the desired variables, it will be something like x of t would be x0 plus 3 multiplied by tf square xf minus x0 t square plus 2 by tfq, or it's a minus actually, xf minus x0 t cube. So this is how our third order polynomial uh, would look like, a cubic trajectory planner would look like, provided initial and final velocities are 0 and our initial time is also considered to be 0. So you can always use this expression if you want to plan a cubic trajectory that starts from x0 and ends at xf, and the total duration would be tf. So that is about cubic trajectory planning. Yeah, and the position velocities and acceleration profiles of this cubic planning. This is how the position profile will look like. This is a third order polynomial, third order, or we could say cubic polynomial. And if you take the derivative of this curve, you would get something like this. This is a second order curve or a parabolic curve. Right? It starts from a zero velocity, and it gradually moves all the way, and at some point it reaches its maximum velocity, then it gradually decelerates. And this is our acceleration profile. This is nothing but a first order or a linear polynomial or a linear system. So again, it also jumps to at initial position. It initially jumps to a finite acceleration, then it gradually decelerates, and at the end it suddenly jumps to zero acceleration. So here also there is actually a finite instantaneous or a sudden jump at the initial and final positions. But in a way, it's somewhat better than the straight line interpolation, where it was, very huge, infinite, infinite accelerations at the start. At the Here it is more or less, it's more or less finite. And if you increase the time for the joint or the end effector to move from one position to the final position, this finite jump will also come down, because TF is actually in the denominator. If TF is increased, this value will be decreased. Okay, so yeah, that is about cubic trajectory. But what happens if you have multiple points like this? If this is your initial point, and if this is your final point, and the joint that you are planning the trajectory on, it is also desired to visit or go through each of these individual points, v1, v2, v3, right? So your desired path of your joint should be something like this. It should go through all these points. We call these intermediate points as via points. So there are actually two ways of doing this. So two ways of doing this actually. So the principle is simply nothing, simply planning a proper cubic trajectory in all of these sections. Between xi and x1, you can plan a cubic trajectory, because between v1 and v2, you can plan a cubic trajectory. V2 and V3, again, you can plan a cubic trajectory. And V3 and XF, you can plan cubic trajectory. So the procedure is same as before, what we have discussed earlier. But there are two ways of doing this, which are the first case being the velocities of the k via points are specified. That is one way. And the second case is the velocities at k via points are not specified. So earlier, with just 2 points, we specify the positions, initial position, initial velocity, and we specify final position and final velocity. We plan a cubic polynomial with those two endpoints. But if you take a look at this case one, it basically means we only specify the position of this via point. And sorry, if you take the case one, the velocities are also specified. So if you take this via point, its position and its velocities are specified, and same for all the three via points. Their positions and velocities are specified. And in case two, their velocities are not specified. So what we do is that we do this interpolation in a way that the final velocity of this segment, the segment between xi and v1, is considered to be the initial velocity of the segment of the next segment between v1 and v2. And the velocity basically propagates from this initial point all the way to the final point. That is the second way of doing it. And the thing is that if you go by the first way, there could be discontinuities between joint accelerations across the wire point. The acceleration may not be a smooth curve. It may have jumps as it moves from the first segment to the next segment. Right? And in case two, the final velocity and acceleration of the wire point will be equal to the initial velocity and acceleration of the next segment. So we won't probably do any problems on this example, but numerous MATLAB examples are already provided during the lectures. I know how these things happen. And if you want to carry forward the velocities from first segment to the second segment, how to do that. All this has been discussed actually. So just to give a brief idea about what will happen if the via point velocities are specified. So if you consider this point to be the initial point, x0, and this point to be the final point, xf, and let this be the via point, xv. So what you can do is you can, just like what we have discussed earlier, you can define a polynomial between x0 and xv, and another polynomial between xf and xv. And if you take the derivative of this curve and if you plot it, you will get the velocity profile that would look something like this. So initial velocity profile would look something like this, and the final profile would look something like this. And as you can see, there is a steep point, a steep sort of a point, like a discontinuity at this location. And again, if you further differentiate these two curves or these two equations and plot it, this is what you get. Two straight lines with a finite or with a huge jump in between the transition point. So this is what happens if you force your joint or your actuator to go through a via point, and if you try to force a specific velocity at that via point, it'll have an acceleration at this point, and suddenly it will jump to a different acceleration, and it will reach a via point. So as it goes through this via point, it will have this sudden jump or its sudden jerk. So the motion will be very jerky as it goes through it individual via points. And what happens if the via point velocities are not specified? You can similarly interpolate a polynomial like this. where the final velocities of the first segment would be propagated as the initial velocities of the second segment. And if you plot the velocities, it will be something like this. Again, it looks to be very smooth. And
Excuse me, sir.
accelerations, if you again take the derivative of this curve, you will get something like this.
Excuse me,
As you can
sir.
see, there is no sudden jump or no discontinuities in the acceleration profile. It goes linearly like this, and from here it goes through the final acceleration with a linear profile. And there is no
Sir,
sudden jump in this acceleration. So this is
sir,
much better in that regard compared to when you specify the via point velocities.
sir. How
Yeah.
is the
Then so far we have only seen trajectory planning using a third order polynomial. So a same scheme we can also use a higher order polynomials. Okay, we have a question actually. Uh,
uh, sir?
we'll move on to
How is this?
the address question. Yes.
How is this
What is your question?
music, polynomial?
How is this different from a cubic polynomial? Which one? The higher order polynomials.
Via points. Velocity is not specified. The just previous slide.
Okay. I'm not sure if I correctly understood your question. Uh,
What is the
it's
difference
nothing. It's
between
just an
in
extension of a cubic trajectory planning, right? Like in cubic polynomial, what we have discussed earlier only considers, only considers an initial point and a final point, right? But with via points, like in practice, you may want to go through some more points before you reach your final position, right? For example, if you have some obstacles in between something like this, you may want to go through these via points for maybe some safeties. What additional inputs are given? You are given the positions of the via points. That would be the inputs. Maybe x v1, x v2. Yeah, velocities are not given. Positions are given. Like as I have said, there are two ways of doing it. With the velocities are specified, without the velocity specified. But the positions are always specified because you want your robot R to move through all the via points. Maybe some due to some practical constraints. If you cannot move, like this through a straight line, you may have to move like this because there could be some obstacles or some other constraints, right? So yeah, this is how there are two ways of doing this. Yep. Positions are always specified, but velocities can be specified. It may not be even specified. And if the velocities are specified, if you want the manipulator arm to reach this via point with a particular velocity of your choice, the problem is that if you take a look at your acceleration profile, there will be a jump. Whereas if you leave the velocities alone, if you simply uh, consider the final velocities of the first segment to be the initial velocities of the second segment, then there may not be any, sudden jump in accelerations. It depends upon your priority. If you want to control the velocities, you will have, jumps in acceleration. Or if you don't really want any specific control in velocities, but you only want to go through these via points, then you will get a smoother, acceleration profile. So I hope that is clear. Okay, so yeah, okay. So now we can also move on to higher order polynomial planning. So instead of a third order polynomial, we can always go for fifth or seventh or higher order. Practically, we would also go for fifth order trajectory planning. We call this quintic trajectory planning. So the general form of quintic trajectory planning is something like this: a0 plus a1t plus a2t square plus a3t cube plus a4 t to the power 4 plus a5 t raised to 5. So this is a fifth order, or we call this quintic trajectory plan. So what are the benefits of a fifth order trajectory planning compared to a third order trajectory planning? So the main benefits is that earlier, like just for reference, I'll also reproduce. I'll say this as the fifth order. I'll also write here the third order curve. Bx of t would be nothing but a0 plus a1t plus a2t square plus a3t cube. So one difference is that, as you can see, there is a lot more unknown coefficients, right? So there are 6 unknown coefficients. So you require 6 equations. Yeah, I got an answer. For quintic polynomial, the accelerations will also start from 0. Yeah, that is correct. That is correct. Because if you take a look at this quintic, the third order polynomial, the acceleration profile would look something like this. It will have a sudden finite acceleration at the beginning and a sudden finite acceleration at the end. But in case of a quintic polynomial, the position is actually a fifth order polynomial like this. Velocity would be a fourth order polynomial like this. And acceleration would be a third order polynomial like this, something like this. So even accelerations also have 0 acceleration at the beginning and 0 acceleration at the end. So, but the major advantage is that it may not necessarily have 0 acceleration. The thing is that it's only a special case that it can have 0 acceleration. So the main difference or main advantage is that here there are 6 unknowns. We need 6 equations actually to solve these 6 unknowns, and the 6 equations can be the initial position velocities and acceleration requirements, as well as the final final position velocity and acceleration requirements. So if you have a specifications of position velocity and acceleration, this cubic polynomial can conform to that specification. Sorry, the quintic polynomial can conform to that specification. Whereas in the case of a third order, we cannot have any control over accelerations, right? We can only have 2 boundary conditions at the start and 2 boundary conditions at the end, right? Position and velocity at the start, position and velocity at the end. So 4 equations. So we don't have any control over accelerations. But in case of a quintic, we have control over acceleration. So like if you desire your acceleration to start from 0, you can actually force that specification onto that quintic trajectory planner. Or if you want to start your acceleration at a desired value, you can also do that through the specification. So in summary, it says, for an n-actuated jointed manipulator, the cubic joint space scheme is very efficient. Cubic is much easier to plan because it only deals with a fewer equations. However, it can only satisfy at most 4 constraints, right? It can only satisfy 4 constraints because there are only 4 unknowns in this, right? If you try to satisfy more number of constraints, it becomes an overdetermined problem. So it may not even satisfy at all. So it can only exactly satisfy 4 constraints. That is, it does not have any control over initial and final accelerations. That is for the cubic. So in this case, we can actually go for higher order polynomials. For example, a fifth order quintic polynomial, where we can have control over accelerations also. So it has control over initial and final accelerations, but it will involve more computations, right? You can see how many terms are here. And if you want to solve these unknowns, 1, 2, 3, 4, 5, 6, you will have to invert a 6 by 6 matrix so that you can actually find these coefficients. So it's computationally more important. Okay, so yeah, this is how these are the boundary conditions of your quintic trajectory planning. You will have your initial position, initial velocity, initial acceleration. You can also specify your desired final position, final velocity, and final acceleration. And yeah, if you substitute these values and the corresponding time into these equations, this equation plus its derivative for velocities and its further derivative for accelerations, you will get these sort of equations actually. 6 equations. So it's a 6 by 6 matrix, 1, 2, 3, 4, 5, 6. And to find out these unknowns, you will have to invert this matrix and multiply with this boundary conditions. So in that case, you will be able to solve this unknown coefficients. And yeah, this is how the profiles would look like. The position profile is like a fifth order polynomial. This is actually a fourth order polynomial, and this is a third order polynomial. So you can actually control your initial positions. You can also control your initial velocities. You can also control your initial accelerations. Okay, so far we have actually covered uh, a straight line interpolation. Okay, so I'm getting a question. Why are you getting second in third row? I didn't follow that. A second in third row, which one?
Yeah, in that matrix. Yeah, there.
Are
Yeah,
you
right.
getting a 2 into
You
third
get
row?
one there.
I
Third row, you
hope
should get.
this is what you are asking.
Yes, you should get one there.
So yeah, I'll try to, if that is what you're asking, I'll try to address that. So a quintic polynomial is something like this: a0 plus a1t plus a2t square plus a3tq plus a4t to the power 4 plus a5t to the power 5. Yeah, if you take the velocities, x dot of t would be a1 plus 2a2t plus 3a3t square plus 4a4tq plus 5a5t to the power 4, and x double dot t would be 2a2 plus 6a3t plus 12a4t square plus 20a5t cube, right? So if you substitute, if you are talking about the third equation basically corresponds to the initial acceleration. So if you consider your initial time to be 0, at time t equals 0, if you want your initial acceleration to start at 0, x double dot of t t0 should be 0. If this is your specification, and if you substitute this condition t as 0 onto this equation, what will you get? X double dot of t of 0 as 0 would be equal to, will be 2a2 plus all the other terms has t, so all these other terms will be 0. So 2a2 would be 0. This is what you will get for this acceleration. So simply writing this as a matrix and vector form. So this corresponds to A1, this corresponds to A2. So this corresponds to A2, yeah, A0, A1, A2, and all the other terms are 0. So yeah, this equation written in matrix and vector form corresponds to the third rule. That is where this 2 comes. Okay, I hope that is clear. Okay, so and so far we have actually covered what have we covered? We have covered the straight line interpolation, we have covered a third order polynomial interpolation. Then we have also seen the fifth order case. And another case of interest or a very common choice is something called a straight line interpolation with parabolic blends. So straight line on its own is not desirable because of the sudden infinite accelerations at both of these ends. But there is a workaround actually. If for the majority of your trajectory, you can have a straight line like this, but towards the beginning and the end, you can actually have a parabolic curve, a smooth second order curve like this. So it actually begins from the initial position. It gradually goes to some position. Then from here, it will go to this position along a straight line. And from this position, it will gradually, like parabolically decelerates to the final point. So if that is the case, how would so I'll label this times of interest as 0, EB, TB, and this would be TF. So this time period, over here from the initial position to the position where it starts a straight line trajectory, we would call this as the time for blending, actually. This is a time for blending. And this is also another time for blending, actually, to decelerate into its final position. So if that is the case, how would the velocity profiles look like? The velocity profiles would look something like this. So since this is a straight line, its derivative would be a constant, right? This is first order, this would be a constant. And since this is second order parabolic, this will be linear, linear increase in velocity, a constant velocity, then a linear decrease in velocity. And if you again take the derivative of this curve, you will get the profiles for acceleration. So since this part is linear, you will get a constant acceleration like this. And since this is constant, its derivative would be 0 like this. And since this is again linear, you will get a negative constant acceleration like this. So your acceleration profile will look something like this: constant, 0, and constant for that time period. And this is also somewhat efficient because you don't have uncontrollable accelerations, but here also there is actually discontinuity. But since this is very popular, this has also been used in a lot of practical applications. But in these exams and all those things, you would probably be given with, an initial position x0. You will also be given with, okay, so I've got a question. If you are driving a car, how do you get infinite acceleration? Zero acceleration and parabolic blend acceleration in practical situation. So in your car, you won't get infinite acceleration at any point, right? Because the thing is that if in your car, it's you yourselves are actually giving the input. But in case of a robot, if you are actually commanding a robot to give a certain acceleration, your gains will be going uh, to an infinite level, actually, to have that sort of infinite acceleration. So it'll be very disastrous if you are trying to implement a control scheme or something like that. If your gain actually tries to shoot to that high infinite level, it can have some disastrous consequences, actually. But in case of a car, it's I don't know. I'm not sure if I understand if I understood the question, because your car cannot actually start. You cannot practically command your car to start from a velocity of 50 kilometer per hour, right? It's not possible for your car to start immediately at 50 kilometer per hour. But in case of a robot, if you are actually asking your robot to go to 50 kilometer per hour, and if the robot is not, and because of its inertia and all those things, because of its feedback, what can the controller do? The controller will try to increase its gain, until that sort of uh, acceleration is demanded. So it can have disastrous consequences if you try to control a car. Sorry, if you try to control a robot manipulator. But yeah, in practical situations, it's mostly relevant to control systems. Something that you try to actuate using controls. But in case of a car, that's not possible because you yourself are trying to give this input, not controller, or not not as per an algorithm or something like that. The thing is, if you're trying to drive a car, even if you're trying to automate a car, and if you're trying to force your car to reach if you are trying to force your car to follow this trajectory, and if some sort of microcontroller is actually commanding a car to do something like this, it will try to maximize, or it will try to increase its gains so that it can at least try to realize that it obviously it'll not reach. It's not possible because nothing can reach this infinite acceleration, right? Because of the inertia of the moving parts, because of the friction in the gear trains, all these sort of things makes it physically impossible for it to be physically impossible to be reaching an infinite acceleration. But you keep on commanding it, you keep on demanding for more power, and what will happen eventually everything uh, will be burnt off, right? So like if you are putting a huge load on a small engine, what will happen? Eventually the engine will fail, right? So similar thing, like the engine will not be able to push a huge load, an enormous load. It will try to do this, and eventually it'll die off, or it'll get destroyed. That's what it happens. Or a similar thing, like if you try to hold a motor, or if you try to block a motor with like huge force, it may have some fail-proof mechanisms to save the motor. But imagine if there is no safety mechanisms, what will happen? If the torque is too high for a motor, you know it'll burn off, it'll get destroyed. So all these situations are to be avoided. So like here also that is the case. Like if you try to command something that is not physically possible, it can damage it can lead to a lot of damage, right? If you are actually commanding, so the bottom line is that if if you try to give if you try to give some constraints, maybe initial position and final position, through a straight line interpolation within a finite step, uh, and yeah, and as a consequence, as a consequence, it will lead to infinite acceleration. If you try to implement that on the controller, it will also try to command the motors and actuators to increase the gain as much as possible. It could be beyond its capability, and finally it'll die off. That is how that is how it's going to end up with. But it cannot, obviously, it cannot reach that much acceleration. No systems can reach infinite acceleration because it will, before that, the system will fail. Okay. So, yeah. So, where were we? Yeah. So, in this case, the typical problems that you could face is that uh, you would be given an initial position. You would also be given a final position. Sorry, xi would be initial position and xf would be final position. And you will also be given a cruising velocity or a cruising speed. I'll write this as the cruising speed, right? The cruising speed is nothing but the constant velocity from which the mechanism or the variable moves from this point to this point, this velocity, this cruising velocity. So if you are given these three parameters, you will be asked to find out this time for blending. How do you do that? Like if you have your goal position, if you have your initial position, if you also have your cruising velocity, how much time do you require to blend to this cruising velocity from zero, and uh, to blend from this velocity to your final goal point? How do you do that? So you will be asked to find out this spot, this time, TB. We'll call this as time for blending. So how do you do that? So to do that, there is actually a small derivation. Uh, should I go for this small derivation? It will only probably take 5 minutes, or do you only need the final formula for this time for blending? Uh, okay, so since it only takes 5 minutes, I'll go for this. Or if you don't want this, let me know. I can skip over this. Yeah. So in that regard, we'll go with this time for blending, probably. Yeah. Let me, yes. So I am considering, yeah. So like I have mentioned, there are multiple times of interest. So this, you could consider this to be this PB1, the initial blending time, and this to be PB2, the final blending time. And let this be your, or you can actually consider it to be symmetric. Most of the time it will be symmetric. TB, TB, and let this be the final position, XF, and let this be the initial position, XI, and this would be the final time, TF, and this would be the initial time, TI. So yeah, the blending would look something like this. Initially, it will be a parabolic curve, something like a parabola. Then from TB to this second point, it will go like a straight line. Then from this point to this point, it will be again parabolic, something like this. And yeah, so we'll have to see this analysis in three different options. The first would be from time 0 to TB. Then the second interval would be TB to TF minus TB, right? Then the third interval would be TF minus TB to TB, right? So 0 to TB would be this interval. Sorry. 0 to TB would be this interval. Just, yeah, this is 0 to TB interval. And TB to TF minus TB would be this interval. And TF minus TB to TF. I think I made a mistake. Yeah, TF minus TB to TF would be this interval. So if you consider the first case from 0 to TB, we have space? Yeah. So how do you write this x of t? X of t would be a parabolic curve. So you can write it, you can actually write an equation of a parabola that will be xi plus some constant kt square. Why not? And velocities x dot t would be 2kt, right? So I'll label this blending points as, I'll call this point as point A and I'll call this point as point B. And this position, I'll call this as XA. And this position, I'll call this as XB. So what will happen at time t equal to TA? I substitute simply the time TB into this equation, into the previous equation, this one. So x of A would be x of I plus ktb square. That is one equation. And velocities, xa dot would be 2k multiplied by ta. And we also know that velocity is the cruising velocity. That is nothing but omega. If you are given this cruising velocity, omega as cruising velocity, okay, so I'll also mark this equation. We'll
Sir,
leave that
I have a
aside.
doubt, sir.
Now, if you
Sir.
consider the time period
Sir.
from TB
Sir.
to TF minus TB, this point. So for time from TB to TF minus TB, what will the equation look like? It's a straight line. This would be a straight line. So you can simply write that equation as x of t is nothing but omega multiplied by, xa plus the cruising velocity, omega multiplied by t. This is the equation for position. Yeah, this is nothing but the equations for position during this period, and velocities x dot of t would be nothing but omega. So if that is the case, then what will be xb? Xb would be x of t. If you substitute that into, if you substitute the corresponding time onto this equation, you will get, you will get x of a plus omega multiplied by change of time. Change of time, final time would be TF minus TB, and initial time would be TB. Because this point is TF minus TB and this point is TB. So simplifying this, you will get it as XA plus omega multiplied by TF minus 2TB. This is your XB. Okay, now that you have XB also, XB is also there. Now, how would you get XF? The final position. XF would be nothing but XB plus XF minus XI. I is the initial position. So the thing is, up to here, we have already written an equation. up to here, we have written an equation, and we need this much distance also to get the final x. So the distance between xb and xf is same as that of xi and xa, right? So that is why I have written it like this, because of the symmetricity. Xf is nothing but xb plus this distance, sorry, this distance, xa minus xi. So substituting all these things, xf is nothing but xb plus, sorry, this is xa minus xi. So xb, I'm writing it from this equation. That is nothing but xa plus omega multiplied by ef minus 2tb, then plus xa, I can probably write it from our previous equation, this equation actually, xi plus or I'll just carry forward that xa for the time being, xa minus xi. So if I expand this, what will happen? Xf would be, you will have xa and xa here. You can write it as 2xa plus omega multiplied by ef minus 2tb minus xi. So for this xa, I'll carry forward this xa from this previous equation, this one, the parabolic equation, right? So if I write it as xf as 2 multiplied by xi plus, what was that? Ktb square, right? Ktb square plus omega multiplied by tf minus 2tb minus xi. So our unknown terms here are tb. Tb is what we are trying to find out, the blend time. So we also don't know this k. So we can actually obtain this k from this from this velocity equation, because omega is known. So k would be nothing by, this is supposed to be tb, the blend time, omega by 2tb. That is what the k is. So if I again substitute that back, you will get it as 2xi plus omega by 2. The tb and tb square will get cancelled, so I'll leave it like that. We'll have only a singular tb. So omega multiplied by tf minus 2tb minus xi. So on expanding, simplifying, you will have this 2xi and minus xi. You will get this as xi. Then this 2 and this 2 get cancelled. You will have omega tb here plus omega tb, plus you will have this omega tf minus 2 omega tb minus xi. This would be xf. Sorry, I already took this xi. So what can I do next? Have I made a mistake somewhere?
We have to simplify now, sir. Xi minus omega
This,
tb. Omega tb minus
yeah.
2
So
omega tb.
I can simply cancel this plus omega tb and minus 2 omega tb. So I'll rewrite it over here itself. I'll write it as minus omega tb. So from here, if you simplify an expression for tb is nothing but xi minus xf plus omega tf by omega. So this is actually a very relevant equation, very important equation. this one. Because what we obtain by this TB is nothing but the blend time, right? So the problem would be something like this. If you are given an initial, I'll go to this graph. If you are given this initial position like this, initial position is, you have a desired initial position, you have a desired final position, and you are also given this cruising velocity omega, then how much time should you spend, or how much time is required for this blending, this much blending, this initial blending and this final blending. And this blending is actually obtained, the time for blending or this TB is obtained by this formula, which is given as xi minus xf plus omega multiplied by tf. Tf is the total duration of the parabolic blending, sorry, the entire trajectory divided by omega. So yeah, that was about it. So now we move on to our slide. I'll rewrite that equation here, PB as xi minus xf plus omega df by omega. This is the time for blending. Okay, so one more final trajectory planning that we would like to discuss here is what we call as the cycloidal motion. So as you know, how a cycloid, what basically is a cycloidal motion. So if you consider a circle rolling over a straight line, so the locus of a point on a circle, the trace of this point, as the circle rolls on a straight line, basically describes this cycloid. So as the circle rolls, this particular specific point, if you label it as A, the locus of the point traced by that point A gives you the cycloid. And that is also a very smooth, like a kind of a curve. So basically, you can write this equation for the cycloid as, so if you consider the two adjacent positions like this, so if I consider this to be the initial position xi, and if I consider this to be the final position xf, and this was this initial angle, and at some other time it reaches this point. During that time, it has rolled over an angle, probably you can call this as alpha. So the distance that it has moved from this initial time, I'll call this as Ti, we'll call this as Tf. So the distance it has moved, you can write it like this, x of t as the initial position xi plus this entire distance from here to here. I'll label it probably. Yeah. So this entire distance is given by r multiplied by alpha, right? If alpha is the angle, alpha is the rotation angle, and if r is the radius, here to here, all the way here is nothing but r alpha. And this much, this point from here to here is nothing but r sine alpha. So you have to subtract it from r alpha. Or you can write it as xi plus r multiplied by alpha minus sine alpha. because the point of interest would be initially here and at the end it will be here. So we are actually interested in this distance. So this distance is obtained by subtracting from this total distance. Sorry, yeah, this total distance subtracted by from this distance. So this is the general equations for the cycloid, the point traced by this point. If I call this as point A, this will be that point A at some other time. And how do you relate this alpha to this time? So, alpha is proportional to, 2 pi if alpha is the angle that it moved over time t, and 2 pi is the time it rolled over a full cycle, a full rotation for a duration tf. Then alpha is nothing but, if you cross multiply, you will get 2 pi t by tf. A simple proportionality actually, because at time t, it will roll only alpha, and for a full duration tf, the cycloid will roll one full rotation. And again, for a full 2 pi rotation, the circumference would be 2 pi r, and that is nothing but, the full circumference would be nothing but the final position minus initial position, right? And from here, this r is nothing but xf minus x0 by 2 pi. So if you substitute this r here and this alpha onto this equation, this alpha and this alpha, at the end, you will get this final expression, something like this. X of t is x of I or x of 0 initial time, plus this term over here. This is nothing but r, and this term is alpha. This term is also alpha. So this, you can write it as x0 plus r multiplied by alpha minus sin alpha. So that is the governing equation for a cycloidal motion. And if you take the derivative of this, you will also get the velocities. Okay, yeah, just for completion, we'll see the profiles. So this is the position profile. Velocity profile, as you can see, it is also very smooth. Acceleration profile is also, as you can see, it's also very, very smooth. Okay. Now a few more schemes. Actually, there are 2 schemes. I'll go through this quickly. Just as I've told earlier, in the case, you can either plan the trajectory in joint space, or you can either plan the trajectory in task space. For example, in case of a 2R robot like this, you have the joint variables like this, θ1, this could be θ2, and you have the task space variables x and y. So if you want to plan a trajectory of your robot to move from this point, I'll label this as xi, yi, initial point. If you want the robot to move to a final point, xf, yf, you can either plan this trajectory in task space variables, xi to xf and yi to if. You can do that way, or you can plan the trajectory in task space, So if you know this xi, yi and xi, yf, you solve the inverse kinematics to find θ1 and θ2 initial, and θ1 and θ2 initial, θ1 and θ2 final. And you can plan the trajectory on theta variables, θ1 initial to θ1 final, θ2 initial to θ1 final. So both ways you can do that. So the first scheme is called joint space, or you can do it in task space. And there are a few subtle differences between those 2 kinds of trajectory planning. Because in task space, it is more easier for us to visualize. Because if you simply plot the motion of a robot on a piece of paper, it's very easy to represent it is very easy to represent the coordinates of the center vector as x and y coordinates. And you can easily visualize, as it moves from your desired position to your final position. But it's not very straightforward if you visualize it in terms of θ1 and θ2 angles. Right? If you want your robot to move from one desired position to another desired position, it's very easy to define in terms of x and y Cartesian coordinates, but it's not so intuitive if you define in terms of the joint space variables. So in that regard, the task space variables are more natural, more intuitive for operator to specify. They are easier to see and visualize. And the thing is, it can have some difficulty in planning orientation, right? Because x and y does not really accommodate the orientation in that regard. Yeah. And traditionally, there are two ways you can do this. You can either go for this straight line interpolation, or you can go for the circular arcs. For example, if you have two positions, xi and yi, and you have a final position, xf and yf, you can actually you can do this as a straight line interpolation, or you can do this as a circular arc. So the thing is that in straight line interpolation, you first plan xi to xf using any interpolation of your choice, maybe straight line or maybe cubic or fifth order or cycloidal. You first do that. After that, you can find out this position of yi from this xi, so that xi and x and y basically form a straight line. That is how you can basically do that. Or you can also do that in circular arcs. Maybe you first define xi and xf using any of the previously discussed interpolation method, and you follow yi such that it follows a circular arc kind of a thing. Xi square plus yi square is 1, or maybe some other radius r square. You can find out this yi square by 1 minus, maybe this r square minus x square, the whole square. This will give you your yi. That is this circular arc interpolation. Either ways, you can do that. So there are a few issues in case of planning in task space. So one such issue is that task space trajectory with non-reachable points. So if this is a 2R manipulator, this disk is actually representing its workspace. This 2R manipulator can only reach points within this disk. It cannot reach this point. It cannot reach this point. It can only reach points within this disk. So if you try to plan a straight line trajectory from this initial point x0 to this final point xf, if you try to plan something used in task space, you may encounter this problem. It may try to reach points that is not reachable. Up to here it is okay. From here to here it is not possible because it's outside the workspace. And from here to here it is also possible. So there is a region of issue that we may have if you try to plan a trajectory in task space like this. So that is one issue. Another issue is the task space. If you try to plan a task space, it may actually go near a singular point. So in case of a 2R robot, the singular points are so this is a generic 2R robot. Singular points are when the arm is fully stretched like this. This is the first link and this is the second link. So this is one singular configuration. Another singular configuration is when it is fully folded. So this is the first link and second link is something like this, fully folded. So these two are singular positions. And you may be wondering why you have a full disk over here like this instead of a donut shape like this. The thing is that donut shape of a workspace exists when the links are of unequal length. Right? If the first link is larger than the second link, your workspace will be of a donut shape. But in case if both of the links are of constant length or identical length, you will have a full disk kind of a workspace. And another issue, the second issue would be, if you try to plan a path from this initial point to this final point through a straight line, eventually it will reach a point where this arm, would be fully folded like this, right? For example, if you talk about a point here, this point, xs and ys, the manipulator would look something like this. The first arm would be like this. The first arm would go like this, and the second arm would go like this. It will be fully folded. So that also is a singular configuration. And that may theoretically reach infinite velocities on the joint variables. Right? At this position, the joint variables theta1 and theta2, their velocity theoretically may go all the way up to infinity during singular configurations. So that is also one another issue. These things we have to avoid these singular configurations when we are trajectory planning. So this is one thing to avoid singular configurations. Going out of workspace is something that we need to avoid. And the third case is, the possibilities of ending with other inverse kinematic solution, right? So if you try to plan a path like this, or I'll use a different ink, a straight line path like this, right? See, if you can see this, there are actually two inverse kinematic solutions for this arm. So if this is this initial configuration, I'll reproduce it like this. The first link is red and the second link is blue. So if this was the initial inverse kinematic solution, it should have reached this point like this. It should have reached that point something like this. This is how it should have reached that point with this configuration. You know what? If you simply rotate it, if you simply rotate this entire arm, it'll end up like this, right? There is no change of assembling or anything like that. But in reality, what happened? It ended up like this, right? It ended up like this. So it changed its inverse kinematic configuration from this configuration to this configuration, right? So it may not be desirable for a lot of times because you always assemble or you always begin your configuration, or you always assemble your manipulator in one particular configuration, to have some advantages, maybe to avoid some obstacles or something like that. But once it reaches some singular points, or once it reaches some, point of issue, it'll go from this configuration to, the other solution, or from this configuration to this other solution. So that also may not be ideal in a lot of situations. So that is also another possibility if you are trying to plan a trajectory in task space. So the first case was, possibility of going out of the workspace. Second case was possibility of achieving a singular configuration. And the third case is possibility of ending with the other inverse kinematic solution, which may not be always desirable. Okay, so we will conclude our sessions with some sample tutorial problems. We have maybe half an hour left. we have 12 questions, so most of them are pretty much
Sir,
non-numerical.
sir,
So the first question is actually the specification of a robot position and orientation as a function of time is called path. That's false. That is indeed false. It's actually called a trajectory. That is correct. Yes. And moving on to the second question. For a cubic trajectory planning, the acceleration profile may contain discontinuities across the wire points if the wire point velocities are specified. Is that correct or is that not correct? So if you try to force some velocities to the wire points other than its naturally occurring velocities, would there be a chance of discontinuities? There will be, right? Should be. There will be discontinuities. So that is true. The statement is actually indeed true. We have discussed in the beginning of our lecture, but please always let me know if you have any concerns. Okay, so moving on to question 3, it says the initial position of a single degree of freedom, a prismatic joint is 10 centimeters. So I'll write this as x initial to be 10 centimeters at time t is 0, and the joint reaches the final position. So xf is 20 centimeters, and the final time is 2 seconds. So using linear interpolation, determine the position of the prismatic joint at t equal to 0.5 seconds. So like there are plenty of 12.5. Yeah, but how do you do that? Because you start from an initial position 10, final position is 20. The total time is actually, it starts from 0. It ends at time is as t as 2 seconds. Yes. So like since this is a straight line problem, one way you can do is that 0.5 seconds. So 2 seconds and 0.5 seconds, you can actually divide this into four equal divisions. Sorry. Right? Because if you consider this to be 0.5 seconds, this to be 1 second, this is 1.5. Since this is linear, maybe here in the middle, it will probably be 15. And here at 0.5 seconds, it will be 12.5. That is indeed correct. I believe that is indeed the correct answer. Yes. You can do it this way, or you can always go for that formula. X would be x0 plus xf minus x0 by tf minus t0 multiplied by t minus t0. You can always use this straight line equation. All the values are actually given. T is your point of interest, that is 0.5. You can also plug in that values and still you will be able to obtain this value. So we have already obtained the correct answer. So that is indeed correct. Okay, so now moving on to question 4. It's a true or false statement. The best trajectory between the 2 points is based on a straight line interpolation in terms of smoothness. Okay, the best trajectory. It says the best trajectory between 2 points is straight line interpolation. So what are the problems of straight line interpolation? If you call this x0, if this is xf, this is T0 and Tf. If this is the position profile, velocity profile would look something like this. Constant velocity. And the acceleration would look something like this. It'll have some huge infinite vertical jerk like this at the start and at the end. And then in between, it will have zero acceleration. So as you can see, it's clearly not the best scheme in terms of smoothness, right? So you can always discard it, and the answer, it has to be false. That is for question 4. It's indeed false. Now moving on to question 5. If the initial and final positions are x0 and xf, and both initial and final velocities are 0, so I'll write this down. X at time t is equal to 0 is x0, and x at time t equal to tf is xf, and velocity at time t is 0 is 0, and the final velocity at time t is tf is also 0. And the time for the total trajectory would be tf seconds. Then the cubic polynomial function can be written as, which of them would be the correct answer? So the only way possible is to at least to remember the correct formula, or during this exam, if you have provisions to do this symbolic inverse of a matrix, then you can also proceed that. So for example, a general cubic polynomial would look something like this. X of t is a0 plus a1t plus a2t square plus a3t cube. And the velocities x dot of t is a1 plus 2a2t plus 3a3t square. So I'll label this as condition 1, label this as condition 2, I'll label this as condition 3, and this as condition 4. So if I apply condition 1, what will you get? We'll get x0 as a0. If I apply condition 2, you will get a1 as 0 as a1. And if I apply condition 3, you will get xf as a0 plus a1tf plus a2tf square plus a3tf cube. And if I apply condition 4, you will get 0 as a1 plus 2a2tf plus 3a3tf square. So if I apply all these 4 conditions, arrange it as a matrix and vector form, I'll have the coefficients a0, a1, a2, a3. On the right hand side, you will have x0, 0, xf0. So it'll be like 1, 0, 0, 0, 0, 1, 0, 0. Then 1 tf, tf square, tf cube, 0, 1, 2 tf, 3 tf square. So if you invert this matrix and pre-multiply it with this vector, you will get the corresponding coefficients of a0, a1, a2, a3. And once you get those, you back substitute it into this general equation, you will be able to get the correct answer. It should be one of these 6 equations. And I believe the correct answer is should be option A, I suppose. Question 5. I think it should be option A. Okay, that is indeed the correct option. Okay, moving on. It's a numerical problem. We can probably use the previous expression. So the initial joint position is given as theta I is 20 degrees. The final position, theta F, is given as 60 degrees. If the initial and final velocities are 0 and the total trajectory is tracked for 4 seconds. So TF is 4 seconds. What will be the maximum velocity of the trajectory if the cubic polynomial is used? So you are asked to find out the velocities actually. So how do you do that? So since the velocities, initial and final velocities are 0, you can always carry forward this expression. So I'll write it over here. X of t as x0 plus, I think it's 3 by tf square, xf minus x0, this will be t square minus 2 by tf cube, x0 minus xf, t cube. So if I take the derivative of this with respect to time, the velocity is nothing but 6, is it 6 by tf square, xf minus x0 multiplied by t minus 6 by tf cube, x0 minus xf, t square. And you are actually asked to find out the maximum velocity. And if you can recall, the maximum velocities occurs, or most of the cases in cubic cases, maximum velocity occurs at halfway around. If you can recall the velocity profile, it looks something like this. And the maximum velocity always happens at around tf by 2. So yeah, or if you are not sure about that, you can take the derivative of this, equate to 0, and from this equation you can find the time at which velocity is maximum, and then substitute back that specific time onto this equation. That is one way. So if you substitute this expression, so but t equal to tf by 2, we'll get max velocity. So what will be that? So if I substitute everything, it will be 6, xf minus x0 would be 40, and half of 4 seconds would be 2 seconds. We'll have here EF square, that will be 16 minus 6 multiplied by, will be x0 minus xf, that is am I using the correct equation? Sorry, it's xf minus x0 here. xf minus x0. So again, minus 6 multiplied by 40 by 64, 4 cube, multiplied by 2 square, that is 4. So if I simplify this, what will you get? I can take this 60 into 40. So if I can also multiply this by 4, by 4. So what will you get? 60 into 40 into 4 by 64 into 40 into 4. So it will be like 2 minus 1, I guess. So what would be the correct answer? So let me check. 60 into 40 into 4 by 64.
Sir, it is 6 na sir. Why it is 60? It is
Yeah. So I probably may have made a small silly mistake. Instead of the 6, I have, for some reason, I have taken it to be 60. So yeah, it's just 6 into 4 into 40, right? So if you do this, the correct answer would be 15, right? So if you are confused by this, it's nothing. You have the position equation. You take the derivative of this, you will get the velocity equation. And for the velocity equation, if you want to find the maximum velocity, substitute this t as pf by 2, then substitute all the given values, initial position, final position, and the total time. You will finally get the maximum velocity value. So I believe the answer is 15 degrees per second. We'll check that. Yes, that is indeed the correct answer. More than average velocity. What do you mean by average velocity? More than average velocity. So I'm not sure what you. Okay, but how do you calculate this average velocity? It's parabolic, right? How do you calculate this average velocity? You will have to probably integrate it, right? How did you? I don't know. I don't know how you calculated that. 50 minus 20 divided by 4. Sorry, 60 minus 20 divided by 4. Okay, so yeah, probably that could be another method. But 60 minus 20 divided by 4. Okay. Oh, so simply you took this average. I'm not sure whether that will be always be feasible, because 60 minus 20 by 4 would always, you know, that can only work when you have a straight line, right? Final position minus initial position by 4. But I'm not sure whether that will always work. It could be dangerous in that regard. It could be, yeah, more. You only said more than average velocity. Yeah, so that's correct. It's 15 in that case. Yeah. Okay, so moving on to question 7. In the case of a single rotary manipulator, the initial joint position is given as 30. Theta I is 30 degrees. And the final joint position is given as 70. And it reached its final position in 20 seconds. So TF is 20 seconds. And the motion is supposed to be a third order polynomial. Further, the initial and final velocities are 0. Then the joint position can be written as. It can be written as. So since this is also a given condition, initial and final velocities are 0, you can again carry forward the same expression. X of t is x0 plus 3 by t square xf minus x0 t square plus 2 by t f cube. Sorry, it's minus xf minus x0 t cube. So if you substitute these appropriate values, what will you get? So x0 or yeah, maybe probably confused with the change of variables. I'll write this as x0. This is xf. This is tf. So yeah, substituting this, we'll get 30 plus 3 by 20 square. That is, I'll write it directly as 400. So xf minus x0 is 70 minus 30, that is 40. And t square, you are only asked to find out this expression. So t square, I can write it as t square itself minus 2 by tf cube. So that'll be 20 cube, that is 8,000 multiplied by 40 into t cube. So this will be 30 plus 0.3 t square minus there will be 80 by 8,000. That will be 0.001 t cube. That will be your final equation. Make use of answer options. Yeah. So in that regard, I think the correct answer is option B. Yes. So question 8, I hope it is clear enough. If it is not, I'll read out the following question. Given below the time trajectory of a straight line planning with parabolic blends. So here it is straight line, and at the ends you have this parabolic blends. From the following options, choose the correct velocity profile for the same. Right. So this is, if it is not clear enough, I can try to make it more clear. It's a straight line. Here it is parabolic. This is this initial time. This is the time for initial blend. This is the stopping of the linear motion, and this is the final blend. So out of all these options, which would be the correct answer? So this is option A, velocity profile for option A. This is option B. This is option C. This is option D. This is option E. And this is option F. What would be the correct answer? Okay, so you have mentioned it to be option C. Yeah, that is indeed the correct answer, because we have seen this exact same during our discussions. This portion is actually parabolic, so velocity would be a straight line. And this portion is a straight line, so velocity would be constant. And this portion is also parabolic, but decreasing, so velocity would be decreasing. So that would be our velocity profile. It's pretty straightforward. So yeah, that is indeed our answer. Moving on to question 9. It's again a true or false. The joint space trajectories lead to look more natural than the task space trajectories, because the end effector is moving smoothly with respect to environment, even if the joints are not. What does look more natural? So if you have a 2R manipulator like this, call this X comma Y. And if you call this to be the joint variables, theta1, theta2. So which would be more natural actually? Would it be natural if you plan the trajectory in task space? Because your ideal ultimate objective would be to guide your end effector from an initial position to a final desired position. So the operator will always be tracking everything in terms of Cartesian coordinates, X and Y. So either you can directly plan this trajectory in Cartesian coordinates, or you can use the inverse kinematics and find θ1, θ2 for this initial position. And for the final position, you can again use inverse kinematics to find θ1 and θ2 final. Then you can actually plan a trajectory in from θ1 to θ1 initial to θ1 final, θ2 initial to θ2 final. But it actually says which is more natural or which is more intuitive. Whether is it planning in task space or is it planning in joint space? So in this regard,
we will do the
there's no answer. I'll say to be true.
inverse
Sorry, it should be false actually.
inverse
This task
kinematic.
space, planning in task space is actually more natural because we get to see, how the path would look like. If you want to plan a straight line, you can actually see, how it would look like. But if you plan in joint space, it may go in some other way. We may not be able to. We may not wish. It won't be possible to visualize. How it will go from this position to this position. It'll be a bit difficult to visualize that. Yeah. So yeah, that is what the answer is. It's actually false. So if you have any doubts on that question, you can always ask. Because planning in planning in joint space, maybe θ1 and θ2. If you plan something in joint space, if you plan a straight line path in joint space, in task space, it may look something like this. It may not be even straight line, right? So if you plan trajectory in this thing, we may not know how it how it may behave in task space. So this is joint space. This is task space. Right? If you plan a straight line in joint space, we probably won't be able to visualize how it will be moving in, how it will be moving in task space. Because maybe if there are some obstacles, defined on task space, if you plan a trajectory, it may collide with this obstacles. But if we plan a trajectory in task space itself, we can actually see, it moves from this point to this point in a straight line. And all these things we can actually visualize, but not in the other case. Okay, so question 10. For a single rotary link manipulator, the initial joint position is 30 degrees. Theta I is 30. And the final position is 70 degrees. And time to reach its final position is 20 seconds. And motion is supposed to be cycloidal. Again, it asks you Vmax. So T for Vmax, again for cycloidal, we also know that it should be df by 2. That is 10 seconds. And our cycloidal equation is something like this. Theta of t is, general form is theta I plus r multiplied by alpha minus sin alpha. Or in terms of the position coordinates, it will be like theta f minus theta 0 by 2 pi multiplied by 2 pi by tf, 2 pi t by tf minus sine of 2 pi t by tf. So if you take the partial derivative of this with respect to time, theta dot of t, so this is nothing but theta f minus theta 0 by 2 pi multiplied by 2 pi by tf minus cos 2 pi t by tf multiplied by 2 pi by tf. So if I take this 2 pi by tf outside, you will get theta f minus theta 0 by 2 pi multiplied by 2 pi by tf. This will be 1 minus cos 2 pi by tf into t. So these 2 pi and 2 pi will get cancelled. So I'll write this tf over here. So to find the velocity, we have to substitute this t as tf by 2. So once I am doing that, tf by 2. So this 2 and 2 will get cancelled. This f and f will get cancelled. So you will end up with theta f minus theta 0 by tf 1 minus cos pi. So cos pi is minus 1, right? So this entire term will become 2. So if you substitute your final answer, it will be 70 minus 30, theta f minus theta 0 by 20 into 2. So this is 4 degrees per second. That is your maximum velocity. So option C. I think it is option 8. Sorry, option 4. Option B. Have I made any correction mistakes? Let me check the answer. It's indeed 4. I thought the calculations are correct. Like Vmax for cycloidal is nothing but theta f minus theta 0 by df into 2. I guess. Okay, so moving on to the second to last question. The problem with joint space trajectory planning is that trajectory can go beyond the workspace, even though the start and end points are fully within the workspace. Like we have seen this example of a donut, where if you have a robot manipulator like this, so this is your initial point, xi, yi, and if this is your final point, xf, yf. So if you plan a straight line from this initial point to the final point, there is a possibility that it may, go out of this workspace. So is this a problem with joint space trajectory planning or task space trajectory planning? See, the thing is, joint space trajectory planning, theta I, joint space planning always happens on joints. Yeah, everything would be feasible. If you are planning in joint space, it will be feasible. There is no limitations or no restrictions on the joint angles. The only rotation would be, the joint limits, maybe in practical situations. But if you plan in task space, this is actually a task space implementation, initial point to the final point, a straight line. So this is clearly implemented in task space, a straight line implemented in task space, and it can actually go out of the workspace. Right? So yeah, that could be this is actually a reason for, this is actually a problem with task space trajectory planning, not for joint space trajectory planning. So I think this entire statement is false because it only applies for task space, not for joint space. I hope that is clear. So moving on to the final question. Yeah, if we define a variable u as t by tf, where u is element of 0 to 1, then the cubic polynomial function can be written in a nested form. Which of the following is given? So the reason that we are doing this is that we actually know that the cubic trajectory planning would be something like this. X of t is x0 plus 3 by t square xf minus x0 t square plus 2 by t cube minus 2 by t cube xf minus x0 t cube. So the problem with this scheme is that if the time is actually very large, these terms can probably vanish, which may lead to some, incorrect convergence or incorrect interpolation. So to tackle that problem, we bring a new variable u as t by tf. So when time t is t0, u is t0, and when time t is tf, u is 1. So that is that variable. So now we can actually define a new trajectory as function of u to be b0 plus b1u plus b2u square plus b3 u cube. And you can rewrite this equation in this form: b0 plus u multiplied by b1 plus u multiplied by b2 plus u b3. It's like a nested form. And these are same equations. And the reason that we are doing this is because the computational cost is actually much cheaper, because you only need 3 multiplication and 3 addition in this case. But here you can see how many divisions, and there are divisions, multiplications. Here itself there is 2 multiplication, again multiplication, again multiplication. Then you have to add it. Here also several multiplications. But here you only have 3 multiplication and 3 addition. This is the first multiplication, first addition. This becomes second multiplication, second addition. So third multiplication and third addition. So it's computationally much more cheaper actually. And if you're dealing with a large systems, computational time and computational expenses will be much efficient if you are using this scheme. Yeah, so that is about it. And I think the correct answer in this regard is option F. Yes. Okay. Yeah, that is true. Yeah, so that is about it. I think we have pretty much covered explanation of question 8 in assignment 5. Assignment 5, the thing is, I'm not sure if the assignment 5's deadline is over or not. Has the answer key been released?
Yes, sir. Yes, sir. It is over. We know the answer, but
If the
I need
answer key is not released,
explanation.
then I cannot disclose any answers here now.
Answer is disclosed,
The
sir.
thing is,
I
I
will
have to
share, sir.
check whether it is disclosed or not.
Sir, it is disclosed, sir.
And the thing is,
I
we
will
are also
share.
not supposed to discuss our current assignments during this session. And in case if you need any more further clarification, you can email me or probably raise that in the discussion forum. We can have a look at that in the Google group. You got the result. Okay, so you want an explanation for that. But I don't know the question actually. I don't have the questions at the moment. I don't have the question. Could you dictate the question? What is the question? Because I don't have the question with me now.
I will share the screen, sir. Hello?
Assign
I will share the screen, sir.
question 8.
Sir,
Yeah, you can share the screen if that is possible. I'll stop mine. You can share. In the meantime, let me see if I can find it on my own. Assignment. Okay, I have to permit you to share the screen. Okay. Yeah, you can. I suppose you can share it now. Week 5 is week 5. Can you share your screen? Or let me question 8 assignment 5. Okay, so question 8, I think assignment 5, question 8, it's about the single link connected to a revolute joint, angular velocity, angular acceleration, all these things are given, center of gravity is given. What are the components of linear acceleration at center of gravity? Is that the question? I hope that is the question. Let me share my screen. Hello? You are not audible, madam. I think I'll share my screen now that I have uh, now that I've found out the question. I'll share my screen. That is okay.
sir, sir, whether you are able to see the screen.
So I believe the question is, yeah, you have a single link like this. Sorry. Yeah, I hope this is the question. I cannot follow the chat. I cannot follow the chat because I'm going through a different screen. So I hope this is the question. X0, Y0, you have a center of gravity over here, like so. Yeah, and the angular velocities are given as 4 radians per second, and angular acceleration is given as 5 radians per second square. Okay. And the center of gravity is also given as, okay. the angular velocity and acceleration with respect to center of gravity is actually given as 2 millimeters along x1 axis. If this is x1 axis, this is y1 axis. What are the components of linear acceleration at the center of gravity with respect to the local link frame one? I think that is pretty straightforward, right? Components of linear acceleration, it will have two components, right? It will have omega cross acceleration, I guess. So it will have alpha cross r. This is the tangential component. And you will also have omega cross r. This is the radial component. Right? And omega 1 is, since it's a revolute joint, it's 4K. And alpha is 5K. And R would be 2I. So I think if you do this vector operation, you will be able to get the correct answer. I suppose that is how you solve it.
Actually, I got
Is that
10,
fine? Is that a good
10,
explanation?
10 plus. Actually, I got 10 plus. But here the answer is 32K. Like that one, the answer is.
Okay.
There is an expression, there is a formula for this one, but I am not able to guess the vector direction, sir. Here, what is the vector direction for first term and what is the direction for the second vector like this one? Now,
So
how we got K? How we got K here? K. K is
because
the
there is an arrow here actually. The joint is a revolute joint, right? It says it's connected to a revolute joint and it's rotating in a counterclockwise sense. And if it is rotating in a counterclockwise sense, if this is x0 direction and if sorry, I'm not sure if I'm sharing the correct screen. Yeah. So there is an arrow in the question that is shown like this, which indicates that it is rotating in the counterclockwise sense. So if this is x0 and if this is y0, z0 should be towards us, out of plane, right? So the angular velocity, everything would be along the positive z axis. So
okay, sir. Okay.
z0 and z1 both are same. Both are along towards us, perpendicular to the point of the plane.
So now, sir, alpha is in which direction, sir? Alpha cross R.
Alpha is in
Al-
plus k. Alpha is in, alpha is 5k along z direction.
Alpha
It's
is in
revolute
K
joint.
direction. Is
Yes.
K direction. And
Yes.
what is R direction?
R would be along x-axis. X1 axis.
Then
X1
what is the
axis would be
cross?
2I.
What is the cross of K and I?
It'll be J, right?
Yes,
K cross I is
some.
J.
But then what is alpha cross R?
Alpha cross R would be 5k cross 2I. That'll be 10J, right?
We have to check first of all the expressions. First of all,
Yeah.
what is the first term? We will check. Where I got, I think I is the first term.
These are the expressions actually, alpha cross R and omega cross R.
I omega I is also there, na sir.
I omega I. No, what is I omega?
So here, sir, here the problem is not there. No, we will see.
Okay.
This is the problem. What are the components of linear acceleration?
Yeah, components of linear acceleration. Yes.
What is the acceleration symbol? Acceleration symbol. Is it alpha, sir? Is it alpha?
No,
I
alpha
plus
equals
1, I plus 1
alpha.
alpha, I plus 1 equal to I alpha. Is it right, sir?
Yeah, I don't know if that is the correct expression. I'm just writing it from my memory. Let me check. I plus 1 alpha I plus 1 is I alpha I plus, there is some other term, right? I omega I
Yes,
cross
sir. Yes, sir.
0, 0, theta I plus 1, something like this. I'm not sure.
Yes, sir. Okay, sir. Now we
The
have only one joint, sir. Is it right?
Yes,
We have only one joint.
you have
And
only
then
one
what?
joint. Yeah.
Then what is the first term, sir? What is the first term? Then
See, if that is if
that is K. Okay, sir.
no. If this is the case, if I alpha, if you are talking about the first joint, this is actually the previous joint. You know. So if I plus 1, if you consider I plus 1 to be the first joint,
Yes, sir.
this should be of the zeroth joint. So
So
that should
0,
be
it is
0.
0.
That
Okay,
should
sir.
be 0.
Okay.
But
Okay.
you don't really have to apply this equation. This is, if you want to have the components of acceleration, you only need to apply this elementary equations, alpha cross r and omega cross r, because it is clearly specified that you only need to find this acceleration along. I think in the question it says you have to find it along angular
At
acceleration.
center of gravity with
Yeah,
respect to the link
local frame.
local frame 1.
Yeah, link local frame one. Yeah, so you can express it with respect to x1 and y.
Sir, here 1 omega 1 is given 4 radians, 1 alpha
Yeah.
1 is given 5 radians. Okay, sir.
Yes.
Then how can we do now?
If 1 omega 1 and 1 alpha 1 is given, acceleration, linear acceleration will have two components. That
Okay,
is
sir.
the tangential acceleration and the normal acceleration. The tangential acceleration is alpha cross r. 1 alpha 1 cross that distance 1 r1. Everything is expressed with respect to the frame of reference 1. And the centripetal acceleration would be omega 1 omega 1 cross 1 omega 1 cross 1 r1.
Okay,
That's
sir.
about it. Yeah.
Okay.
This
Then
is how you can.
alpha is K, and you are saying R is in the I direction.
I direction. I direction of this x1 y1 coordinates.
Means
There
what
are
is the
two
final
coordinates
vector?
actually.
Final. What
There
is
are
the final vector direction? Final vector direction then.
final vector direction. Like if you consider I to be the unit vector along x1, j to be the unit vector along y1, and k to be the unit vector along z1, then alpha cross r would be 5k cross, I guess it's 2i, right? It'll be 10j. Then similarly, if you do this omega cross r, you will get something else. I think omega was 4i, right? Sorry, 4k cross 4k cross 2i. So if I first do this, it'll be k cross I would be 8j. And again, you will have this 4k. So 32, k cross j is I minus 32i.
Sir, here the
Sorry. Hello.
Sir, the centripetal acceleration always acts towards the center, whereas the tangential acceleration is always a tangent. Are you able to hear me? This one is muted, sir. Audio is muted. Sir, your audio is muted.
Yeah, I can hear it.
Okay.
Yes.
Sir, centripetal acceleration is always pointing towards the center, whereas
Yes.
tangential acceleration is toward in the direction of motion.
Yeah.
So if you go by that, if you come out of those vectors, the centripetal acceleration is simply omega square r, and
Yes.
tangential acceleration is r alpha.
Yes.
So now if you see in r alpha direction,
Mm.
to draw the curve, it is in the
Mm.
positive y direction. So that gets
Yes.
plus, whereas the centripetal acceleration is pointing towards the negative x direction. So
Yes.
that gets the minus.
Yes. Correct. Correct.
Good
Actually,
minus.
because that is correct. Actually, because if you know the fact that centripetal acceleration is always towards the center, you can simply multiply this. You can always multiply it to be I don't know, what was it? 4 multiplied by 4 multiplied by 2. You will get 32, and you only need to put a minus before it because centripetal will always be towards the center. And since it is towards the center, it is along the negative x1 axis. So that is why we have this minus 32. Or if you are not sure about the fact that it is acting towards the center, you have to do this vectorially. And finally, you will get this answer as minus 32i. Exactly what you have said. So thank you for that. But I don't know if Lakshmi ma'am's doubt have been cleared.
Then how we got, sir? 10, 5k into root 2i. It is it alpha into, is it alpha
Just
into
r
r, sir?
alpha, r alpha,
Alpha
r
into r.
alpha, and you move along
Um,
the circle in the tangential direction in the direction of motion.
Okay, sir.
So that
Thank
will
you, sir.
point you in the y direction.
Okay, but still, I have confusion. I have to practice. Okay, sir.
Yeah.
Thank you. Thank you, sir.
If you don't know that, it's always better to proceed vectorially. Then if you are not familiar with these concepts, if you do this vectorially, vector equations are very important. Their order is actually very important. They are not commutative. So alpha cross r is not equal to r cross alpha. And if you follow this procedure, if you follow all these things, you will get the correct answer with the correct sign, right? Otherwise, if you already knew that centripetal acceleration is towards the center, you could simply multiply the value. You could multiply the scalar value and put a minus before it. Then you will get this minus 32i. And tangential acceleration will always be perpendicular to this link that is along this y1 axis. So you can multiply this alpha and r. Then it will be along this y1 component. That's how you will get this answer. Either ways you can do.
If you have done the engineering mechanics course by Professor Ramesh, he talked about omega cross r. If they're having only one component, like in this case, omega has only k cross I, he said it will be just minus I.
It will be minus I, yes, correct.
That's what he talked in the class.
Yes.
Okay, sir.
Thank you.
Okay, sir. Thank you, sir.
Whereas if it's having I plus j, then it's not approved.
Okay.
K cross I plus j, something like that. Only
Yeah,
here
it'll be
it has
more
only
complex.
one
Yeah.
component, and that R has another component. So,
Yes.
Okay, sir. Thank you, sir.
Okay. Thank you. Thank you for joining in. That's been a long lecture. Okay, so with this, I'm winding it up.
thanks a
Okay,
lot.
thank
Have
you.
a nice
Thank you.
day.
Thank you.